Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we are discussing chemical thermodynamics, and in this chapter we'll be covering the following objectives. In the first objective, we will learn what makes a reaction spontaneous and differentiate between spontaneous and non-spontaneous processes. In the second objective, we will introduce the concept of entropy. We will discuss Boltzmann's constant, and we will explain microstates. In the third objective, we will cover the first, second, and third laws of thermodynamics. In the fourth objective, we will learn how to calculate entropy changes in reactions and also understand entropy's role in determining spontaneity. The fifth objective introduces Gibbs free energy. This is really crucial for predicting the spontaneity of reactions. Then in the sixth objective, we will go over calculating free energy changes under standard conditions. In objective 7, we'll see how free energy is affected by conditions that vary from the standard state. Objective 8 connects free energy to equilibrium, and it's going to show us how these concepts predict reaction behavior. And then finally, we're going to explore how temperature influences Gibbs free energy and the equilibrium constant, and we're going to reveal the link between temperature, spontaneity, and equilibrium. With this introduction, let's get started with objective 1. When is a process spontaneous? In thermodynamics, a spontaneous process is one that, once initiated, can proceed on its own without the need for continuous energy input from an external source. This idea of spontaneity is central to understanding why certain chemical reactions occur naturally while others do not. However, it's important to clarify that in thermodynamics, the term spontaneous doesn't imply that a process starts on its own. Instead, it means that once the process begins, it will continue to completion without any additional energy being supplied. A useful example is the reaction between hydrogen and oxygen gases to produce water. If we ignite a mixture of hydrogen and oxygen, the reaction releases a significant amount of energy as it forms water molecules. This release of energy sustains the reaction until it finishes, and that illustrates a spontaneous process. However, decomposing water back into its hydrogen and oxygen gases requires a continuous supply of energy. The moment we stop supplying that energy, the reaction stops as well. Therefore, breaking down water into its elemental gases is considered a non-spontaneous process. Now, to determine whether a process will be spontaneous, we need to consider 3 primary factors: enthalpy, entropy, and temperature. These 3 factors come together in the Gibbs free energy equation, which is written as change in Gibbs free energy is equal to change in enthalpy minus temperature multiplied by change in entropy. Now, we're going to discuss this equation in great detail in a later objective, but in short, for a process to be spontaneous, delta G must be negative. And this equation shows us why enthalpy, entropy, and temperature are all essential for understanding spontaneity. To quickly define these terms, starting with entropy, entropy is a measure of energy dispersal within a system. So it is the tendency of energy to spread out and distribute as widely as possible. However, a precise understanding of entropy requires a deeper exploration, which we're going to cover in the second objective. Temperature is also important. It plays a crucial role in spontaneity because it can affect the balance between enthalpy and entropy. Now, what about enthalpy? We discussed this in General Chemistry 1, but let's review. Enthalpy represents the heat change in a reaction, and enthalpy can be classified as either exothermic or endothermic. An exothermic reaction is one that releases energy to the surroundings, and that results in a negative delta H. This energy release often makes the reaction more likely to be spontaneous because it drives the system towards a more stable, lower energy state. On the other hand, an endothermic reaction absorbs energy from the surroundings, leading to a positive delta H. Because endothermic reactions require an input of energy, they're generally less likely to be spontaneous unless other factors like entropy favor the process. In summary, determining whether a process is spontaneous requires us to consider enthalpy, entropy, and temperature together rather than in isolation. With that being said, let's move into the second objective, where we're going to discuss entropy. Entropy, denoted as capital S, is a central concept in thermodynamics and again can be thought of as a measure of energy dispersal or the degree of disorder within a system at a specific temperature. More specifically, entropy tells us how much energy is spread out or how widely it becomes distributed among the particles in a system during a process. The more spread out the energy, the higher the entropy. Now, in General Chemistry 1, we were introduced to the following equation to calculate change in entropy. In this equation, change in entropy is equal to Q rev, which is the heat absorbed or released by the system during a reversible process, divided by T, where T is temperature. But a more precise way to understand entropy involves looking at the concept of microstates. A microstate is a specific way in which the energy of a system can be arranged at the molecular level, considering all of the possible positions and energy levels of the particles. The number of microstates, represented by a capital W, reflects the different configurations the particles in the system can adopt while maintaining the same overall energy. The more microstates available, the greater the entropy of the system because there's just more ways for energy to be dispersed. Now, Boltzmann's equation for entropy captures this relationship mathematically in this equation right here. This equation says that entropy is equal to K, which is Boltzmann's constant, and it's equal to 1.38 times 10 to the negative 23 joules per Kelvin, multiplied by the natural logarithm of W, where W is the number of microstates available to the system. So this equation shows us that as the number of microstates increases, the entropy S also increases. Now let's explore this idea further with a simple example involving a two-flask system containing 4 gas molecules labeled A, B, C, and D. Let's imagine these 2 flasks are connected by a valve, and the gas molecules can move freely between the flasks. We can then calculate the number of possible microstates by considering how the 4 molecules could distribute themselves between the 2 flasks. One scenario is that all of the molecules are in one flask. We can have all 4 gas molecules on the left side and none on the right, so that gives us 1 microstate. Or we can have all 4 gas molecules on the right side and none on the left. That gets us a second microstate. So for this scenario, that all the gas molecules are in one flask, we have a total of 2 microstates. What about the scenario of having 3 gas molecules on one side and then 1 gas molecule on the other side? This can happen in a number of ways. We can have those 3 gas molecules on the left side and 1 on the right side, and that combination gives us a total of 4 microstates. We can have ABC on the left and D on the right, or we can have ABD on the left and C on the right, or we can have ACD on the left and B on the right, and finally we can have BCD on the left and A on the right. So 4 microstates for the combination of 3 gas molecules on the left, 1 on the right, but we can alternatively do 1 in the left, 3 in the right, and that gives us also 4 microstates. We can have A on the left and BCD on the right. We can have B on the left and ACD on the right. We can have C on the left and ABD on the right, or we can have D in the left side and ABC on the right side. So for this scenario of 3 molecules on one side, 1 on the other, there are 4 microstates for each configuration, totaling 8 microstates. So 2 plus 8, so far we have 10 microstates. We can also have the combination of 2 molecules on each side, 2 on the left, 2 on the right, and this gives us a total of 6 microstates for this arrangement. If we have AB on the left, we can have CD on the right. If we have AC on the left, we can have BD on the right. If we have AD on the left, we can have BC on the right, and so on and so forth for a total of 6 microstates. So when we add up all of the possible configurations, we find that there is a total of 16 microstates for the 2-flask system. And this calculation illustrates how the number of ways we can distribute particles between 2 flasks directly correlates with the entropy of the system. The more ways to arrange the molecules, the higher the entropy. With that being said, there's also a few more general conclusions about entropy we can make. The first point I want to make deals with temperature dependence. So for any given substance, increasing the temperature increases the number of accessible microstates because particles gain energy and can now occupy a wider range of positions and energy levels. So in short, entropy generally increases with temperature. The second point I want to make deals with states of matter. Gases typically have a higher entropy than liquids, which in turn have a higher entropy than solids. This difference arises because particles in a gas are free to move and occupy a vast number of positions, thereby creating far more microstates than the relatively fixed particles in a liquid and solid. The final point deals with mixing and solutions. So when a solute dissolves in a solvent, the system's entropy usually increases because there are now more ways to arrange the particles in the combined solution. The mixing process disperses energy more widely, thereby increasing the number of microstates. Keeping these 3 points in mind, let's tackle a practice problem. This problem wants us to determine the sign of delta S for each of the following processes. In A, we have liquid water is converted to ice. Now, liquid has a higher entropy than a solid. Therefore, when liquid water becomes ice, the entropy decreases. So delta S is less than 0. In part B, we have iron and oxygen gas reacting together to form iron 3 oxide. What we notice here is that we have 3 moles of gas on the reactant side, but none on the product side. The entropy of gases is much higher than that of solids or liquids, So the reactant side here has a greater entropy. This means that as the reaction proceeds forward, the entropy decreases in this reaction, so delta S is less than 0. Finally, part C says 50 grams of liquid water at 75 degrees Celsius is cooled to 25 degrees Celsius. We said that for a given substance, if the temperature increases, then the entropy increases. Now, the opposite is true. If temperature decreases, then entropy also decreases. And that's what's happening in this scenario. So delta S is going to be less than 0. With that, we've solved this problem, and now we can move into the third objective, where we're going to discuss the laws of thermodynamics. Let's start with the first law of thermodynamics. The first law of thermodynamics is also known as the law of energy conservation, and it states that the energy of an isolated system is constant. In simpler terms, energy cannot be created or destroyed. It can only be converted from one form to another. Mathematically, we express this in the following form. Delta E system is equal to negative delta E surroundings. Delta E system is the change in energy of the system, and delta E surroundings is the change in energy of the surroundings. This equation shows that any energy lost by the system is gained by the surroundings and vice versa. This law is foundational in thermodynamics because it reminds us that all energy exchanges are balanced. Energy doesn't just disappear, instead, it transforms or transfers. The second law of thermodynamics builds on this concept by introducing entropy. It states that in any spontaneous process, the total entropy of the universe always increases. And this is represented in the following way. Delta S of the universe is equal to delta S of the system plus delta S of the surroundings, and this is always greater than 0. Here, delta S of the universe is the change in entropy of the universe, and again, it includes both the system and its surroundings. For a process to be spontaneous, the total entropy change must be positive. And this law is crucial because it sets the direction for spontaneous processes, and it reinforces that nature favors dispersal and disorder. Finally, the third law of thermodynamics gives us a reference point for entropy. It states that the absolute entropy of a pure, perfectly ordered crystalline substance at absolute 0 is 0. At this point, the particles are in their most ordered state, and there is only one possible microstate leading to 0 entropy. This law helps establish a baseline for entropy values, and it allows us to quantify entropy changes by comparing them to this 0 entropy reference at 0 Kelvin. Together, these three laws form the foundation of thermodynamics, and it shapes our understanding of energy, entropy, and the conditions for spontaneity. From here, we can move into the fourth objective. With our understanding of entropy established, let's move on to entropy calculations. In thermodynamics, calculating the entropy change for a reaction allows us to quantify how the disorder or energy dispersal in a system changes as a reaction proceeds. The standard entropy change for a reaction is defined as the entropy change when all reactants and products are in their standard states. Standard states refers to a specific set of conditions, and those conditions are as follows. Every gas exerts a partial pressure of exactly 1 atmosphere. Solids and liquids are in their pure forms at 1 atmosphere pressure. Solutes in a solution have a concentration of 1 molar, and the temperature is typically set to 25 degrees Celsius, which is equal to 298 Kelvin, unless otherwise specified. The equation to calculate the standard entropy change of a reaction is given right here. This equation says that the standard entropy change for a reaction is equal to the sum of the standard molar entropies of the products, each multiplied by their respective stoichiometric coefficients, minus the sum of the standard molar entropies of the reactants, each multiplied by their respective stoichiometric coefficients. In simpler terms, to calculate the standard entropy change for a reaction, we first multiply the standard entropy of each product by its coefficient from the balanced reaction and add them up together. Then we do the same thing for the reactants. And when we have those two things, we can subtract the total entropy of the reactants from the total entropy of the products. Let's take a look at a practical example to see this calculation in action. Let's consider this reaction of iron and oxygen gas together to form iron 3 oxide. To calculate the standard entropy change for the reaction, this is going to be equal to 2 times the standard molar entropy of iron 3 oxide, which is our product, minus this term right here. This term is equal to 4 times the standard molar entropy of iron plus 3 times the standard molar entropy of oxygen gas. These are the reactants. All right, and these two quantities are subtracted. So we subtract the total entropy of the reactants from the total entropy of the product. Now, understanding the standard entropy change for the reaction alone, however, is not enough to determine spontaneity fully. The second law of thermodynamics teaches us to consider the entropy of the universe. Now, the total entropy change for a spontaneous process, that's determined by the sum of the entropy changes in the system and its surroundings, and we can mathematically write this in the following way. Delta S of the universe is equal to delta S of the system plus delta S of the surroundings. For a process to be spontaneous, delta S of the universe must be positive, meaning that the entropy of the universe increases. Since we already know how to calculate delta S of the system for any chemical or physical change, we should also learn how to calculate delta S of the surroundings. And we can do so using the following equation. Delta S of the surroundings is equal to negative delta H, this is the enthalpy change of the reaction, divided by T, which is the temperature in Kelvin. This formula relates the entropy change of the surroundings to the heat absorbed or released by the system. So when a reaction releases heat and is exothermic, it increases the entropy of the surroundings. If a reaction is an endothermic reaction, then it decreases the surroundings' entropy. And by combining these calculations, delta S of the surroundings and delta S of the system, we can determine the change in entropy of the universe for any given process and use it to begin to assess spontaneity. Now, what we're going to do is jump into a practice problem, but I do have one more thing I want to note. Keeping track of both the system's entropy and the surroundings' entropy can become pretty complex. And this is going to lead us to a more practical thermodynamic function called Gibbs free energy, which will simplify spontaneity predictions by just combining enthalpy, entropy, and temperature into a single equation. That's going to be the exact focus of the next objective. But again, for now, let's jump into a practice problem for this objective. This problem says, consider the following reaction carried out under constant pressure conditions. We have nitrogen gas reacting with oxygen gas to form nitrogen dioxide. We're also given the change in enthalpy for this reaction. Then we're asked to figure out what the value of delta S surroundings is at 298 Kelvin and to figure out if this reaction is spontaneous. Let's start with part A. To calculate the change in entropy for the surroundings, we use the following equation: negative delta H divided by T. Delta H is the change in enthalpy and T is temperature in Kelvin. We have both of these variables, so we can go ahead and plug them in. We have negative 66.4 kilojoules divided by 298 Kelvin. When we plug this into our calculator, we get negative 0.223 kilojoules per Kelvin. Now, if we were to rewrite this in units of joules per Kelvin, it would be equal to negative 223. What we notice is that the change in entropy of the surroundings is negative. So let's keep that in mind moving into part B. Is this reaction spontaneous? Now, the second law of thermodynamics says that a process can only be spontaneous if it results in an increase in the total entropy of the universe. So delta S of the universe is equal to delta S of the system plus the delta S of the surroundings, and this has to be greater than 0 for a process to be spontaneous. Now, we figured out from part A that delta S of the surroundings is negative. Now we need to determine the sign of the change in entropy of the system, and we can actually do that by looking at our reaction. On the reactant side, we have 3 moles of gas, and on the product side, we only have 2 moles of gas. Whenever there's a decrease in the number of moles of gas in a chemical reaction, the entropy of the system also decreases. So that means delta S of the system is also negative. Since delta S of the system and delta S of the surroundings are both negative, then delta S of the universe must also be negative. Now, we know that in any spontaneous process, the entropy of the universe increases. So since that's not the case, since delta S of the universe is negative, this reaction is not spontaneous. And with that, we've solved this practice problem. We're going to go ahead and end the lecture here. In the next part, we will finish up our lecture on chemical thermodynamics. I hope that this has been helpful so far. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.